In this video, we're going to discuss force and motion. This is actually chapter 3 in the second edition of the Shiflet book. And some of the topics we're going to look at are just number one, understanding some basic laws of motion and understand the simulation of physical equations and how to apply the if statement within the MATLAB or Octave software to adapt the simulation to changes. So let's start by considering changes within a system. All right. So in this case, we've already done the Super Bowl examples where we had the car and the velocity was changing. But in those cases, we knew ahead of time exactly when and what the change was going to be. And so we didn't really need to worry about it. So now we're going to look at it at a slightly different angle. So what we have here is we have a velocity, and the velocity is going to change. Not only is it changing, but it's going to even just change the whole response or the whole function that it's performing at given certain conditions. Now, in this example, the condition I'm giving is a known time. So when we look at the first example, which is shown in the blue graph down here at the bottom, the first example, we have that we just have a constant velocity. So if you look there, so as we look right here, we just have a simple constant velocity of 2 meters per second. Okay, so this system, it's not even given what the system is, but just a system that just has a constant velocity of 2 meters per second, and it maintains that for exactly 1 second, which of course, right, when we integrate that, we find that it traveled exactly 2 meters. If it was moving 2 meters per second in 1 second, it moved 2 meters. But what we're really concerned about here in this case is that at that time, at time 1 second now, the velocity changes to a function, which the function in this case is just simply time divided by 2. So whatever time it is, we're going to divide that by 2. So therefore, our velocity was at 2, and now we have this immediate change where the velocity actually becomes 1/2. So this is actually a discontinuity in our velocity. So we have this huge jump downward from 2 meters per second down to 1/2 meter per second. But then it starts increasing in a linear fashion. Okay, but the key here is the fact that we know that something caused the system to change and to make this change. In this case, we're basically just given that the change was instigated by, I don't know, somebody flipping a switch or stepping on the gas or whatever the case might be. But we know in this example, we know that happened at exactly 1 second into the velocity response. All right, so it doesn't have to be a time fact. It could be something else causing that change to happen. But this example is just using time. So in the first example, we just have the one change from a constant value of 2 to the time divided by 2. 1/2 the whatever the current time is. In the second example over here in the red, we start off with the exact same change. So we start off with a constant of 2 for the first second. And then at 1 second, we have the change, which is t over 2, exactly like we had over here on the left-hand side, but at the second change, which occurs at exactly 2 seconds, we end up getting another complete function change, which is the cosine of 2t. So we end up getting this cosine change happening here. So again, the point is the fact that we don't necessarily know exactly what the velocity is going to be, but we do know that, due to a certain occurrence happening in this case, we know when the occurrence is happening. Sometimes it might be where it happened as opposed to when, but whatever the cause is, we can then use that cause and trigger that to make the change inside of our simulation. So the way we do that is with an if statement. And the if statement is, you can see down here we have if and then else, and then of course there's an end if. And so what we're doing here with the if statement is we have the we were given in the problem that the change is going to occur. Let me get my arrow here. The change is going to occur at time of 1 second. So I have here in this first plot here, I have that the time, if the time is less than 1 second, right, because I don't show the time here, but if I was using like my normal time step of 10 milliseconds, 0.01 as a time step, so for every t element in my t vector, where the value of t, the magnitude of t is less than 1 second, then my velocity is just going to be that constant value of 2. However, I know then that after that occurs, then my velocity comes into this next, which is the t divided by 2, or I multiplied it times 1/2, 0.5 times t. All right, and so we have an if the time is less than 1, then my velocity is just a constant value of 2. Else, okay, so the else only occurs if the first one is false. So if once t is equal to 1, notice even equal, if t is exactly equal to 1, this first option is false. The first if is false. And so if the if is false, you go to the else. And so then you start calculating the velocity, that your next velocity at step k is going to be 1/2 of the current time. Right? And then from there, you just go on and do a standard integration using Euler's integration as we've done before. So the only thing that we're really doing new here is we're using an if statement to say if some certain instance occurs, then we use this velocity definition. Otherwise, we're going to use this other velocity definition. So we're using if statements. If statements are basically asking a question. If this is true, if it's true, we're going to do the commands below that if. Otherwise, we're going to go to the else and do the things below that. Okay, so we're only going to do one or the other. We're not going to do both with an if statement. All right, so if it's true, we do the things underneath the if. If that's false, then we go to the else. Now, you don't actually have to have an else. Okay, the else is not actually a required part. You need to have the if and you need to have the end, but you don't technically actually have to have the word else here. So what that means, if you don't have an else, then if the if is false, then you just don't do anything. You just move on to the next line in the code. All right, so if you can leave an else out, if you don't need it, then don't put it in there. Now, this was for the blue velocity where we only had the one change that occurred at 1 second. So let's go back and look at that plot here, right? So this was that plot for the first example on the left-hand side here in the blue, and we only had the velocity do the major change at that one time of 1 second. Now the red box over here then shows us for the second example. Here in the second example, right, we had the time changed at, or the velocity made a drastic change at 1 second, and then it made another major change at 2 seconds. So we had two changes in there. So if that's the case, then we have our if statement still, but we also have an else if. So you ask the question, and in this case I was asking the same question. I'm asking the question, if time is less than 1 second, and if that is true, then I'm going to execute this command, which just sets the velocity equal to the constant value of 2. But if the first if question is false, then I'm going to go and ask another question. So I'm going to say, well, wait a minute, that one was false. Let's ask another question. Let's say, and in this case, this question is asking if it's less than 2. Now notice this works because it's only going to get to this one between time 1 and time less than 2. All right, so if I was actually asked the less than 2 question first, if I swap and put the less than 1 as the second one, it would never get to the second one because it only does one of these, and once it finds a match, it exits out through the end if at the bottom, and then it starts executing the rest of the code within the M file. So it's so you have to make sure that you have your logic correct. If I was to put the t less than 2 up here with the if instead of the else if, then it would never give me a constant velocity of 2. So you need to make sure that your logic is orderly and makes sense, and that it will get to that case when it should get to that case. So again, the top one just says if it's less than 1. So if time is less than 1, velocity is a constant. Else, okay, so if that, once time is equal to 1 or greater than 1, then we're going to move into the else statement and ask the question, well, okay, we already know that it's actually greater than or equal to 1 because it failed the first if. So that's the only way we got to the else if choice. But now we're asking the question, well, okay, it's greater than or equal to 1, but is it less than 2? And if that's true, then we get this t divided by 2, or 1/2 times t. But if this is false, so once our time is equal to 2 or greater than 2, then we go into the else statement. Now again, I don't need to have an else if I don't need one, but if you need it, like in this example, I need to have velocity defined in all cases. So in this case, I definitely do need to have the else because I need to have a definition of what is my velocity for all time. So I have to have like the velocity in all cases, but it's different depending on the outcome of the if question. All right, so here are the plots. We have the original velocity plots that I showed a couple of slides ago are down here. So this is the first example where we're velocity is constant at 2 meters per second. So that means it's just increasing at a constant, right? We get this nice linear increase for the first second. But then at the next, at time 1 second, our velocity makes this huge change to be t divided by 2. Well, remember, that's the velocity down here. So when you divide t by 2 and you integrate, you end up getting a parabolic, right? So this is you see the curve here, this is effectively t squared is the solution to t divided by 2. The solution is t squared, so we're now getting a parabolic curve for our position as we move on in time. And so you can see that change there. I've got that marked on the graph there when that happens, right? And then likewise with the second example, we had the same thing here where the velocity was increasing, or the velocity was constant, so our position was increasing linearly for the first second. And then at that change, then we get that parabolic t divided by 2 for velocity. And so we tend to get this parabolic, but we only get that for 1 more second. And then we have the velocity becomes cosine 2t, which gives us this kind of large cosine curve for our velocity. And so when we integrate that, we actually get a minus sine wave popping out of here. And so that's kind of where we're getting this curve here now. All right, so keeping that in mind that we can use an if statement in there, we'll need that obviously for our homeworks coming up. But now let's kind of switch gears here and talk a little bit about Newton's laws of motion. So Newton's first law of motion says that a body at rest will stay at rest, or a body in motion will stay in motion unless acted upon by an external force. Okay, and we're going to have to kind of keep these in mind as we try to build our simulations for the upcoming weeks here. All right, so yeah, so keep in mind that the velocity is going to be the change of position, and also keep in mind that acceleration is the change of velocity. So one of the simulations we're going to be doing here is we're going to simulate someone parachuting out of an airplane and dropping through the air. So if you were ever to jump out of an airplane, you know that you're effectively not moving in the airplane. I mean, you're moving horizontally in the airplane, but vertically, when you're standing in the airplane, you're not moving. But you take one step out of the airplane, and of course, you immediately start dropping. And so not only do you start dropping, but you start speeding up as how far you're dropping, and that speed increase as you're falling is the acceleration of gravity, right? That's acceleration pulling you down. And so you're going to speed up and go faster and faster and faster. However, you're going to reach something that they talk about that's called terminal velocity. And the terminal velocity occurs when your acceleration, which is due to, the mass of your body, and of course gravity. So like if you were on the moon, it would only be 1/6 of what it would be here on Earth, but if you were on Jupiter, I think it's something like 5 times Earth or something. So that acceleration is going to be dependent on whatever body, celestial body is that you're on, but but you're also going to be slowed down. And so you're going to be, what's slowing you down is your air resistance. Okay, so you have gravity as an outside force acting upon you, and then as your speed increases, your air, the resistance due to the air as you're moving through the air is going to try to slow you down. And when those two become equal, then your speed becomes a constant. So the speed is constant. You're still moving, but you're moving at a constant speed. All right, so so keeping that in mind, let's return back to the first law of motion, right? A body at rest stays at rest. A body in motion stays in motion unless you have that external force acting upon you. All right. Now, of course, we always have this external force of gravity acting upon us, unless we happen to, be an astronaut and be up in outer space orbiting the planet or something, and then we don't. I mean, the force is still kind of there, but it's different. All right, but it's this outside forces that are going to cause the body to change its motion or change its speed. All right, and so it's the force is basically an acceleration on the body, or well, the force is basically an acceleration. It's going to cause a movement. It's going to cause it to change. So we know, of course, the first um, force is of course the which is Newton's second law here, right? The force acting on the body is equal to the mass of the body times the acceleration. So when we're talking about, like, stepping out of an airplane and heading toward Earth, the acceleration is gravity. But if we're talking about we're in a car and we step on the accelerator pedal in the car, then we're going to move forward. All right. And so there the acceleration is horizontal, and we don't really consider gravity because we're moving, at least theoretically, horizontal to the direction of gravity. And so it's not changing in the z direction. All right. So, but if we look at force, typically using the SI units, force is measured in newtons. Okay. So we have newtons. 1 Newton is 1 kilogram times meter per second squared. All right. So this is, again, it's this second squared here piece is kind of a hint here that this is a uh, has acceleration in it, right? Because remember, the acceleration is meter per second squared, and then we're multiplying it times the mass, which is kilograms. Okay, so the force is mass times the acceleration, which is meters per second squared. All right, so and now we're to Newton's third law of motion, which says that all forces occur in equal but opposite directed pairs. So if like the reason we're not falling through the floor that we're standing on, even though gravity's pulling us down, so we're not moving. And gravity's pulling us down. So why aren't we moving? Because the force our body is pressing on due to the gravity, our bodies are pushing down on the floor, but the floor then is pushing back on us, so we don't fall through the floor. Right? So so how do we start moving? Well, where does that movement come in then? Then that's where we get the acceleration. So if we have an acceleration applied, that's that external force that actually causes us to move. Okay. So we have to change that, and then we have the acceleration, which is the opposite force. Okay. So remember that the sum of the forces acting on the body is always zero. So if we look back at Newton's second law, where'd that slide go, right? So the forces on the body are always zero. So if that's the case, then how do we find the acceleration? We take the we take all the forces, and if there's any difference in them, then that would be the acceleration, which is going to counteract those other forces. Okay, so This is just a reminder that velocity is a change in position and acceleration is a change in velocity. Okay, so if we're going to step out of an airplane, we're going to have air friction applying to us. So let's talk a little bit about friction. Friction, also known as drag, is a force that is acting in the opposite direction of movement. So it doesn't matter which way you move, you're going to have some friction, which is going to be opposing that direction of movement. All right, and the thing about friction is it's proportional to velocity. All right, now there's a couple of different types of friction, and so the one we're looking at here is what's called Stokes friction, which is proportional to the velocity. So there's a force. Friction is a force, and that force is due, there's a scalar quantity times the velocity, okay? And that scalar quantity there is called the drag coefficient, which of course is going to have kilograms in it, and it's going to be seconds, all right? And it needs to be that because remember that forces are in newtons, which are kilograms times meters per second squared, and the velocity is meters per second. So when you multiply meters per second times kilograms per second, you end up getting kilogram meters second squared. Right? So one of the things you can always do when you're trying to set up your simulation is to keep track of your units and make sure that your units match. So if you have a variable that's supposed to be a force, then you should be having units of kilograms times meters divided by seconds squared. All right, now there's also a Newtonian friction, okay? And so this one's a little bit more complicated here. The Newtonian friction is based on a drag coefficient, but it also takes in account the density. So if you're moving through air or you're moving through water, right, the density is greatly different. And also the area, the cross-sectional area of the object that's moving through there. All right, so we have these, so basically if we go back and we look at this example here of K, K is just the a general drag coefficient. It's kind of a simplified version, but if we look at the Newtonian friction, all right, the Newtonian friction basically separates the drag coefficient so that we still have a coefficient piece, but it also incorporates the density of the material that we're moving through, whether it's air or water or a vat of oil or chocolate, whatever, wherever you might be. And so I don't know if you ever find yourself swimming in chocolate, but I'm sure it's got a different density. And so that's the D piece there. And then the area is how much that's a cross-sectional area that you're presenting to the material that you're trying to move through. And then the other aspect of this, I mean, there's a factor of 2 in here, and then there's velocity squared. All right, so if we use Newtonian friction, then we actually have to deal with the square of the velocity instead of just the first order velocity. All right, so if we are moving through air and we're moving through air at sea level, okay, so this equation here, we have that the force is 0.65 times the area times the velocity squared. This is for movement at sea level. Okay, so the drag coefficient is equal to 1 at sea level for air. So that's kind of where the drag coefficient comes from. And so then that this 0.65 then is basically our density at sea level. So that's the density of air at sea level um, with the drag coefficient of 1. Okay. And the drag coefficient varies depending on the type of material. So if you have like a smooth metal as opposed to bricks or something like that that are very porous, that's going to affect your drag coefficient. But if we make the assumption that we're moving through air at sea level, then we can use this equation here to determine our friction through the air. So as we move through, the faster we go, the more force we're going to have opposing us. Okay, so if we're moving really slow, remember this is velocity squared. So if we're moving really slow, it's not going to be that big of a force, because if we're only moving at say 0.1 meter per second, and you square that, you get 0.01 meter per second squared. And so it's dependent on your velocity. But as your velocity increases, this opposing force, remember we're talking friction, which is opposing our movement. It's always in the opposite direction that we're moving. Okay. So if we are falling through the air, if we're jumping out of an airplane, I don't know if any of you ever had the opportunity to do that, but if you do that, right, gravity is going to pull us down. So notice the negative sign means that gravity is pulling us down. Okay, and it's the acceleration. Now, this isn't a velocity. This is an acceleration. All right, so it's pulling us down 9.81 meters per second squared. So as time increases and we keep accelerating, we keep going and faster, the force due to acceleration is increasing. However, as our velocity increases, we also get this equation, which is opposing that. So when this force here is equal to your acceleration force, then you reach what we call terminal velocity. All right, and so you're still moving through the air, but you're not speeding up. All right, and so you're moving through the air at this speed, which is due to which is controlled by the area and your drag coefficient. Again, we're assuming a drag coefficient of 1, but your drag coefficient plus the area, the cross-sectional area that you're presenting. All right, and so that is controlling that speed. All right, so if we think about skydivers, if you've ever watched a skydiver or if you've done this yourself, when you jump out of an airplane, you start falling pretty fast and you start accelerating, right? You're speeding up. And then, but like you can see, like this group here in this picture, that we've got these skydivers, and they all linked up. So they all jumped out of a plane, but they linked up. Well, how do they do that? Well, one of the things they do, right, is when you jump out, if you like kind of do a head dive and go head first, your cross-sectional area is very small. And so therefore your resistance, your friction is very small. And so you're going to go very fast. But if you spread out your body with your legs and arms spread out as these divers are, you're going to go much slower because you have much larger cross-sectional area. And so you can kind of control your speed by just how you angle your body. Okay. And then, of course, if you open up a parachute, now you've got this huge area of the parachute that is, of course, going to slow you down dramatically. Okay. All right. So given that, okay, we're going to want to accelerate here. So I've got a little video here. We're gonna try to simulate this this maneuver from a movie here called Eraser. All right, so now the link here is right here on the slide. I'm going to kind of open it up and just kind of go through it. We're not going to watch a whole video inside of this video, but I'm just going to move to a couple of points and point out what's happening in here, and you can come to this link and watch it later. Okay, now this is an Arnold Schwarzenegger movie, so of course, you know, there's some gunfire and stuff in here, and you may find it not very realistic, but it's, you know, it's a typical action flick. So all right, so here's this video, and what we have here is Arnold Schwarzenegger, typical type action movie. You know, he's the good guy, and he's in trouble, and he's got to get off of this airplane. So he takes a parachute, and he grabs a parachute in here, and he was going to put it on, but he ends up dropping it, and it falls out of the plane ahead of him. Okay, so what happens? Okay, here actually he kind of falls out of the airplane, but he's barely holding on, and then he grabs the parachute. Right there, he's going to reach in and he grabs for the parachute, but he drops it. So now he's still holding on to the plane, but the parachute has already started falling. Okay, so he lets go of this parachute, and, or excuse me, he lets go of the airplane, and he starts coming down, and he's falling through the air, but the parachute's way ahead of him. Okay, so the parachute is like just way ahead of him, and so he does a head dive here. All right, and you know, so he tucks his arms in and points his head down, so he's going to go much faster until he comes down here and actually catches the parachute. Okay, so he catches the parachute and somehow miraculously gets the parachute and gets it on and pops it open, and there he is, and the parachute's open, and so now he's falling at a safe rate so that he can, you know, get down to the ground and be okay. But the bad guys up on the plane turn the plane around and come after him. Okay, and so this plane comes right after him and messes up his parachute. So he's all tangled up in his parachute, and he starts falling again much faster. All right. And so he struggles with this for a while, and he finally gets it off, and he gets the untangled from the other one, and he pulls his emergency chute. So fortunately, of course, he's got an emergency chute, and he releases that, and it pops open, and then he lands on this car. Okay, so that's just that's kind of the video clip there. Like I say, there's the link, and you can watch the full clip um, yourself on there. But what we want to do is we want to simulate this. So what we have down here is we have the velocity, and this is kind of what your plot is supposed to look like when you're done. Okay, the character in the movie, his name is John Kruger. That's why I've got the name there. Okay, but so this guy is going to jump out of the airplane. Now at time t equals 0, that's when the parachute comes out of the airplane. So the parachute comes out and it starts falling, and you can see down here at the bottom. Okay, so we can see way down, right down here, time t equals 0, the parachute comes out and it's falling. And it's falling faster and faster and faster. So this is the parachute, and it's falling, and it goes faster and faster until right about here. And this is when it reaches its terminal velocity. So what happens here is that the force due to acceleration and the force due to the speed in the area of the parachute have equalized. And so now it's going to maintain, this is Newton's first law, body stays in motion. Okay, so the body stays in motion. If it's in motion, it's just going to stay in motion unless there's an external force. So we have gravity pulling it down, and we have the force of friction slowing it up, and when they equal, that's going to be your terminal speed, and that's why it's constant along there. You have this terminal speed. Now, at this point right here, this is the point where he lets go of the airplane. He's like, that's it. I'm just going, my only chance is to let go and catch the parachute. So at this point right here, all along here where the line is blue up top, John, the character's name is John, so I'll call him John here. So John is right here this whole time where he's constant. He's still on the airplane, or at least holding on to it, okay? So he hasn't begun to drop yet. So this whole time he's just hanging on to the airplane, and so he's not falling. So at this point right here is when he lets go of the airplane and starts his head dive. And so now he starts his head dive. Now he's falling faster than the parachute because his mass is a lot more than the parachute, of course, and he's doing a head dive, so his cross-sectional area is, it's probably actually pretty similar to the cross-sectional area of the parachute, I would say. But his his mass is much more, so he's going to fall faster. So here at this point, he lets go of the airplane and he starts falling. Now he starts falling much faster until he finally reaches his terminal velocity. See, his terminal velocity doing a head dive is way up here at this speed, where the parachute's terminal velocity is much slower because its mass is less. And because remember that your force is due to your acceleration and your mass. So you're going to go faster if you have more mass. All right, so then he starts, so down here he's falling, and then right here at this point is where he catches the parachute. Okay, so he actually catches the parachute. So now, well, actually, he catches the parachute and he gets it on and opens it up. Okay, so he gets the parachute and he gets it on and he opens it up. So now the parachute opens, and so he slows down. So his velocity, now notice the parachute sped up. The parachute was right here, and the parachute did a huge speed increase because he grabbed it. He was going so fast, he basically went right on by the parachute, but fortunately he was able to grab it, and so he grabs it with him. So the speed of the parachute increased dramatically so that they're both going at the same speed right here. So there's actually a little bit of a bump in speed here, but it doesn't, you'd have to zoom in on it to even try to see it. But then, and actually the other thing is that I'm kind of saying he grabbed it and put it on in the blink of an eye, right? So, which, it took him a while in the movie, and of course, if somebody really falling like that, it'd definitely take him more than a second, or I mean, this is actually even in milliseconds or microseconds where he gets the parachute on and open in basically the blink of an eye. But so then the parachute opens, and so now notice him and the parachute are moving the same now because they're fastened together, so they're moving the same. So now he slows down because the parachute's open. so he's moving slower. So you can see here that the parachute is, it's kind of hard to see here, but this line here is a little bit, has a little bit less slope than the parachute's line did before he caught it. Okay, so the slope is slightly different there, but they turned out the way the simulation worked that it's hard to tell that change in difference. But then here's where that plane comes back around and messes up his parachute, and he starts falling again. All right, and now, but see, the thing is, he's falling a little bit faster than he did before because he still has the parachute, and so that's more mass. Okay, and so he has over here, you know, he's falling faster than he was over here because there's a little bit more mass, because there's the mass of him plus the mass of the parachute, and they're both together. Okay, and we're ignoring the extra drag due to the chute actually, you know, trailing behind him a long ways. So at this point, he's falling very fast again, even faster than he was before. And then, you know, he's struggling, and he finally cuts away the part of the chute that's messed up, and then he opens the reserve chute, and then he has a nice leisurely drop, probably a little bit faster because the reserve chute isn't as big as the main chute. But so he's, you know, but now he's falling until he actually then reaches the ground. Okay, so again, this simulation here, your numbers are going to be different than this, but you should have, you know, when you're done, it's, I mean, we're going to do this in multiple parts, but when you're done, your simulation should look very similar to this one. All right, so what we have to do, like all the time, we have to initialize our variables, and then we're going to have to determine, this is the kind of the new part, we're going to have to determine the change in our velocity due to, and we're going to have to use the if statements to find what that velocity is depending on our thing. So in this example here, what's going to, we're going to use if statements to find the times. So I give you in the problem, I give you the times, how many seconds into this certain things happen. And what's going to happen then is the area is what is changing. So remember, our force due to friction, right? The force due to friction is controlled by the area. And so if your area is changing, it's also controlled by the velocity, but it's what we need to worry about in our if statement is the area. It's the area that is going to change. Okay. So when you do an if statement here, you can do like I showed before, like greater than or equal to or less than, as you can kind of see here. If you want to do an exact equality, notice we kind of used this before with the find command. Two equals together are asking the question, is this equal? Is this an equality? A single equal would be an assignment of a variable. So if you want to ask the question, is this variable or value equal to this other variable, then you need the two equals together. Likewise, if you look over here in this code, you see the two ampersigns is an and. So that means that time must be greater than 7 and time must be less than 12. Both of these have to be true. It's an and, so the first one has to be true and the second one have to be true for the if statement altogether to be true. Okay. All right, so you know, if you look in the book, they have this example. They just have a more simple example of them just jumping out and opening the parachute. So we added a little bit more to the overall homework assignment here. But remember that the forces are equal to the mass times the acceleration. All right, and so you don't have any acceleration if all the forces are equal, right? A body in motion stays in motion, or a body at rest stays at rest. So there's no change in motion without a difference in force. So the acceleration, what we're really looking for here is the acceleration. So we actually kind of have to rearrange this and find all the forces acting on the body. So we have forces pulling us down, which of course is gravity. And then we have the forces opposing gravity, which is the friction pushing us up. And so the difference between those will determine your acceleration on the body. Okay. So you just have to, you might, you really need to solve this in several lines. So instead of having a single line where the velocity is equal to this, you probably want to break it down and calculate what is the force due to friction, what is the force, then what is the total forces, and then what's the acceleration. So the acceleration are the total forces divided by the area. Okay, and even though we're talking about somebody jumping out of an airplane who at 5,000 meters certainly isn't at sea level, we're going to just use this simplified Newtonian friction and assume that we're at sea level the entire time. So we'll just keep this value constant for simplicity.